All right, in our first demonstration today for sniffers, we're checking out Wireshark. Wireshark is a free network protocol analyzer. It is mainly used to analyze and troubleshoot network issues, but it can also be used in a malicious way. Interesting, right? To sniff the traffic on a given interface. So we will check out a few options here to configure it, and then we'll try to capture the traffic. Now we'll start here by checking the interface list. Mainly, if you have more than one interface, they will all appear in this pop-up here, and you have to select which specific interface you want to capture on. All right, so we'll go ahead and do that. Now, if you go to capture options, the most important option is the promiscuous mode. Now, by default, Wireshark is using promiscuous mode on all interfaces. What this allows you to do is to capture all the traffic on a given network through your interface. We have to do some ARP poisoning before that. So in this chapter, we will see how to perform ARP poisoning. Now, when we poison a network and use promiscuous mode to sniff on a given interface, we will be able to capture all the traffic directed from all the other computers on the network directed to our interface. So Wireshark is able to capture the traffic of all other computers on your network if you are poisoning that network using ARP poisoning. We'll keep promiscuous mode enabled and we will start to capture. Now remember, we always have to specify the interface that we want to capture on, so start capturing. In the end, when you want to stop the capture, you can save all this information or all the packets to a file and then analyze that later on. Typically, we will see all the communication that's happening on that interface, so why don't we go ahead and try to open a website. Let's navigate over to Google. And we'll see somewhere here the HTTPS and the ARP messages. ARP doesn't actually stop on Windows, so you will always see ARP messages on Windows computers and any other network device. ICMPv6 is still enabled here, and SSDP protocol. Now, as you can see, it's pretty clear. We are capturing all the communication that's now happening on this interface. Now, the trick here is if you are running any unprotected protocol like FTP or Telnet, or if you log in on HTTP session, not HTTPS session, you will be able to see all the information in clear text. So we will be able to capture the username and password used to log into that session. Now remember, I'm only talking about unprotected protocols like Telnet, HTTP, or FTP as examples like I mentioned. So when we use a protected protocol with encryption like HTTPS, SFTP, or SSH instead of Telnet, we will not be able to see the username and password. We will be able to see the session running on Wireshark using Wireshark, but again, we will not be able to see much of the data. So now we know about how Wireshark works in a basic way. We'll come back and continue with ARP poisoning in just a little bit.
Often, network protocols need to transport large chunks of data which are complete in themselves. For example, when transferring a file, the underlying protocol may not be able to handle that chunk size, like limitation of the network packet size, or is stream-based like TCP, which doesn't know data chunks at all. In that case, the network protocol has to handle those chunks itself and, if required, spread the data over multiple packets. It also needs a mechanism to find back the chunk boundaries on the receiving side. A method to do this is TCP reassembling. Wireshark has that ability to reassemble a TCP communication. It arranges all the related packets together in one window, allowing the user to navigate through all the packets in a human-readable format.
That's right. And TCP dump is a common packet analyzer that runs under the command line. It allows the user to intercept and display TCP IP and other packets being transmitted or received over a network to which the computer is attached. Distributed under the BSD license, TCP dump is free software. Now, TCP dump works on most Unix-like operating systems, including Linux, Solaris, BSD, OS X, HPUX, and AIX, among others. In those systems, TCP dump uses the libpcap library to capture those packets. The port of TCP dump for Windows is called WinDump. It uses WinPcap, the Windows port of libpcap. TCP dump prints the contents of network packets. It can read packets from a network interface card or from a previously created saved packet file. TCP dump can write packets to a standard output or a file as well.
It's also possible to use TCP dump for the specific purpose of intercepting and displaying the communication of another user or computer. So a user with the necessary privileges on a system acting as a router or gateway through which unencrypted traffic such as telnet or HTTP passes can use TCP dump to view login IDs, passwords, the URLs, and content of websites being viewed, or any other encrypted information for that matter.
Yeah, that's right. And you can see here several different ways to utilize TCP dump. Now we're going to take a moment and we're going to walk you through what each of these do. First, when you execute TCP dump command without any option, it will capture all the packets flowing through all the interfaces. -I option in the TCP dump command allows you to filter on a particular Ethernet interface. All right, next, TCP dump allows you to save the packets to a file, and later you can use the packet file for further analysis. Third, you can receive only the packets greater than n number of bytes using a filter greater through TCP dump command. Fourth, if you want to know all the packets received by a particular port on a machine, you can use TCP dump command as shown below. All right, Laura, and finally, the packets will have source and destination IP and port numbers. Using TCP dump, we can apply filters on a source or destination IP and port number. This command captures packet flows in Ethernet 0 with a particular destination IP and port number 22.
In computer networking, promiscuous mode or promisc mode is a mode for a wired network interface controller NIC or wireless network interface controller WNIC that causes the controller to pass all traffic it receives to the central processing unit CPU rather than passing only the frames that the controller is intended to receive. This mode is normally used for packet sniffing that takes place on a router or on a computer connected to a hub instead of a switch, or one being part of a WLAN. Interfaces are placed into promiscuous mode by software bridges often used with hardware virtualization.
And in IEEE 802 networks such as Ethernet, Token Ring, and IEEE 802.11 and Infinity, each frame includes a destination media access control address or MAC address. In non-promiscuous mode, when a NIC receives a frame, it normally drops it unless the frame is addressed to that NIC's MAC address or is a broadcast or multicast frame. In promiscuous mode, however, the card allows all frames through, thus allowing the computer to read frames intended for other machines or network devices.
Promiscuous mode is often used to diagnose network connectivity issues, but it can be used in a malicious way to sniff on a network. One may be interested in detecting network devices that are in promiscuous mode. In promiscuous mode, some software may send responses to frames even though they were addressed to another machine. However, experienced administrators, as we are all going to become, can prevent this by using carefully designed firewall settings.
Yeah, and a perfect example is setting a ping or an ICMP echo request with the wrong MAC address but the right IP address. So if an adapter is operating in normal mode, it will drop this frame and the IP stack never sees a response to it. If the adapters are in promiscuous mode, the frame will be passed on and the IP stack on the machine to which a MAC address has no meaning will respond as it would to any other ping. Right? So the administrator can prevent this by configuring his or her firewall to block ICMP traffic. Cain and Abel can reveal which NIC is acting in promiscuous mode. So as you can see, Windows machines that are not sniffing the network normally respond to ARP test broadcast 16-bit and ARP test multicast group 1 only. On the contrary, when a sniffer is activated and the network card is put into promiscuous mode, they start to respond at ARP test broadcast 31-bit as well.